Sometimes people ask for the antiderivative. But instead of talking about the antiderivative, it's probably better to talk about an antiderivative. So why is this the and distinction really important? Because a function can have more than one antiderivative. Let's take a look at an example. Let's think about the function f of x equals 2x defined on the whole real line. Can you think of a function whose derivative is 2x? Now I'm looking for a function which differentiates to give me this function. So here's an example. Big F of x equals x squared, and yes, if I differentiate that function, I get back 2x, which is in fact little f. So the derivative of big F is little f, or in other words, an antiderivative for little f is big F. Okay, good. Now, can we think of another function whose derivative is 2x? Well, yeah, think about this function, big G of x, which I'll define to be x squared plus 17, and big G's derivative is the derivative of this sum, which is the derivative of x squared, which is 2x, plus the derivative of 17, which is 0. So big G differentiates to little f, and that means another antiderivative for little f is big G. Okay, great. Now let's think of yet another function whose derivative is 2x. Yeah, I can play this game all day. Big H of x is equal to, say, x squared plus 123. Big H differentiates to 2x again, so big H is another antiderivative of little f. There's clearly a pattern here, right? What's the general story? Well, here's the general story. So I got this function, f of x equals 2x. Any antiderivative of little f has the form big F equals x squared plus c for some constant c. All of our previous examples had this form, right? Here the constant is 0, here the constant is 17, here the constant is 123. And what I'm claiming here is that any other antiderivative is just x squared plus some fixed number. How do we know this? Well, it goes back to the mean value theorem. So suppose I've got two antiderivatives, big F and big G, for little f. In other words, I mean that if I differentiate big F, I get little f, and if I differentiate big G, I get little f. So suppose I've got two antiderivatives for little f. Now what can I do? Well, I can define a new function, call it big H, and big H will just be big F minus big G. Now what do I know about the derivative of big H? Well, the derivative of big H is the derivative of f minus the derivative of g, because the derivative of a difference is the difference of derivatives. So this is the derivative of f minus the derivative of g. But what is the derivative of f? It's little f. What's the derivative of g? It's little f. This is little f minus little f. Oh noes, this is 0, right? The derivative of big H is 0. Now what does that mean? Well, if you think back to the mean value theorem from earlier in the course, right, if a function's derivative is equal to 0 and say that function is defined on the whole real line, like our example with x squared and 2x, then that means that this function is a constant, right? So that means that h of x is a constant. Now what that means is that the difference between f and g, these two antiderivatives for little f, is just some fixed constant, right? In other words, f of x is equal to g of x plus some constant. And this is exactly what we're trying to get at, right? This idea that if a function's got two different antiderivatives and the function's defined, say, on the whole real line, then those two different antiderivatives just differ by a constant. Or said differently, if you've got a specific antiderivative, then any other antiderivative is just that specific antiderivative plus some constant. Let me say that again and actually write it down. Suppose that little f is a function that's defined on an interval I. That's really crucial that it's defined on an interval. And suppose that big F is an antiderivative of little f. In other words, if I differentiate big F, I get little f. Well, then any antiderivative of little f, not just this one, any antiderivative has the form big F of x plus c for some constant c.